Okay, so welcome along everyone again. Today we have Filippo Massari. He's an old friend of mine from the Australian days and my co-author, as you can observe. So we've got up to an hour from now, Filippo, so over to you.
Okay, thank you very much, Johnny. Always very kind. Thank you for coming, everybody. So today I want to talk about misspecified learning. What is misspecified learning? Misspecified learning is becoming more and more trendy recently in economics. It's just learning in the situation in which we cannot learn the truth. No? Every learning model implicitly or explicitly assume that there is a reference class of statistical model. And if we make the heroic assumption that the true data generating process in this class, we will learn the truth, in most learning situations, unless you are fixated on going to the casino or betting on coin tosses, you cannot learn the truth. The truth is too complicated. There is a nice quote by Box, says every model, statistical model in this context is wrong, but some are useful. Many other fields, including statistics and computer science, have moved over this idea that we learn the true model. And economics is also moving in that direction. And so that's the idea of the paper, focusing about misspecified learning in a way that is a bit more pragmatic rather than theoretical. We do have a body of literature, started with Espondapuzzo, Berknash, that is very theoretical, speaks about equilibrium in specified environments. We don't do that. We care about actual decision. We care about payoff resulting from our action. And the idea that we want to put forward with this paper is that many of the biases that we have found experimentally, they actually are a robust response to the fact that the world is complicated. Robust response means they do better than Bayes whenever we are in a misspecified environment, and they don't do worse than Bayes whenever we are lucky and we are in a well-specified environment where Bayes rule works well. So, a bit of history. Economists, statisticians always use Bayes as a benchmark of rationality for a number of reasons. First of all, because it has a nice axiomatization. You can think of Savage, or you can think about Kolmogorov if you want. Second, because Bayes' rule is time consistent, which is very nice from our perspective, because the time consistent rule typically roll out arbitrage in an equilibrium model. So if you want to do the typical little game that you can do time zero trading or recursive trading and get the same equilibrium, you need to have a time consistent probability measure. Otherwise, this doesn't work. Okay, this is why we like it. Experimentally, however, there is a strong evidence that shows that many people, if not the majority, do not follow Bayes' rule. Most people tend to be, there are a number of learning biases. The one that is typically most robustly found is that people tend to be conservativist, meaning they update their posterior, we would say in a Bayesian terminology, less fast than what Bayes' rule would prescribe. Okay? So, historically, we tend to say Bayes is rational, biases are bad. Think about Kanema-Tversky, this idea that biases are due to cognitive limitation, and since we are limited, we cannot do as well as a fully rational person. Here we are in a different world. We believe the world is not simple. We're not in a small world of Savage. We are in a complex world. We cannot learn the truth. In this world, biases can be good. Biases can give you higher accuracy, return, however you want to measure performance, than being Bayesian. Furthermore, we see that specifically the biases that are documented in the experiments are the one that gives better payoffs. So not only we find that in a world that is more complicated than the small world of Savage, bias learning can be better than Bayes, but also that we do have the biases that are conducive of better performances. This is an idea that resonates with the ecological rationality of the G-Answer, if you want. It resonates with ergodicity economics, this idea that we evolutionary, unconsciously, so not rationally, have habits that allows us to navigate our environment in a way that is even better than the theoretical solution sometimes. And so this is what we're going to do. It's an odd behavioral paper if you want, because there will be a lot of theory. We will show theoretically that biases that are consistent with conservatism can do better than Bayes' rule, and the opposite biases, the biases that we do not observe. The true will be true. This result is true for single biases and for combination of biases. So not only it says that these biases should be around, but it says that these biases should be around in a way that is in a combinatorial way. So they should be present together. They all help each other, these biases. They're not treated independently. Okay, good. Any questions so far? No. I think I already said everything here. We will spend a significant amount of time here because, as I said before, we believe that there is not enough attention dedicated to the problem of misspecified learning. What is the main difference? Well, something that when I was in an undergrad and people were talking about, oh, why behavioral economics is not good? Well, because there is one way to be right and infinitely many to be wrong. So if we start with the benchmark of rational learning in well-specified model, then we know that either you learn the truth or you're dominated. When we don't make any assumption about the true data generating process, it's essential to have a criterion that is not subjective, because if you have a criterion that changes depending on the sequence of realization, or a criterion that assumes implicitly or explicitly that you must know the truth to verify which model is best, then the first one is completely subjective, so it's not suited to give any ground to a formal theory. And the second one is just cheating. I mean, how can you say that a learning procedure is better than another one if assuming that the truth satisfies certain conditions, then it does better? It seems something obvious, but if you think about the way typically people defend Bayes' rule, or not even defend, they just state how great it is. They quote this known result that Bayes' rule converges almost surely according to every model in the support to the true model. Now, converges almost surely at the optimal rate, we can add it, it's true, to the best model, to the true model, true, if you assume that the true is in the support. If we don't know anything about the true, this statement is completely empty. So we'll spend some time about the fitness criterion because it's important not to be circular and not to make statements which are weak. Okay, and then we'll show that the conjecture is correct, meaning that the biases that typically are present in experiment gives an evolutionary advantage over Bayes' rule and the opposite biases. Okay. A bit of notation. So we call, well, we have a state space set of possible outcome, X. Think about coin tosses. X can be head or tail. Think about a dice. X is the number between 1 and 6. There is a probability measure, P. We don't say much about P because we don't want to make assumption about the true probability. And we look at sequences of outcome. So xt is the realized outcome at period t. X apex t is the cylinder between x1 and xt. So the first T-realization or the next T-realization. I always use an abusive notation in which likelihood and probability of cylinder use the same notation. Okay. Theta hat, not sure whether we're going to use it or not in the presentation, is the limit frequency of each state. So suppose you have dice, theta bar 1 would be the frequency of 1, theta bar 2 the frequency of 2, etc. We assume for some of the result that this frequency exists. In fact, all the result in one direction, which I would say, do not even assume that the frequency of states must exist. So you can take any deterministic sequence of realization, everything I say still hold. Okay. What is learning? We adopt the Bayesian notation. So for Bayes rule to be well defined, you need a set of models. We call it M. It's a family, in this case, of multinomial models because we have n possible realizations. Each multinomial model is parameterized by a vector parameter. In a very obvious way, here is the probability of each state. If we talk about the dice, the probability of 1, 2, 3, 4, 5, 6. So each model is characterized by this vector. We do not assume that the truth is in the prior support. It might be, or it might not. We just don't make the assumption. We define, as everybody else, a misspecified learning environment. Not actually everybody else. I just did a referee of a paper in which they were not defining misspecification in the correct way. So a learning problem is misspecified if the truth is not in the support, meaning if you cannot learn the truth. If the truth is not in the support, there is no way in which the sequence of posterior would converge to a Dirac on the true model because the true model is not there. So if it's not in the support, the problem is misspecified. We have a prior distribution on the model set because we make mixed prediction, technically speaking. So we have a possible set of models and we have to decide how much weight to give to each model to build up our prediction. In the Bayesian setting, this is the prior. If it's another algorithm, we just say weight. And we use this ingredient and the realization, this is the typical conditional sign on the past, to construct a prior, and then we use the prior to construct a posterior to make predictions. Okay? This is to show in our notation how Bayes rule look like. So the probability according to Bayes rule of state xt given the past is the prior weighted sum of the model in the support. P theta are the probability that each model theta attaches to outcome xt. Mu b theta given the past is the prior. How the prior evolves? The prior evolves according to Bayes rule. The weight on model theta equals the probability of theta divided the Bayesian probability times the prior. This is just the way Bayes rule evolves. Nothing new. It's just to get used to the notation. If somebody has a question about the notation, it's better if you speak now or just stay silent forever.
Sorry, yeah, I had a question, not so much about the notation, but to understand. So this probability. So say I would know that the right parameter is theta, right? The probability that xt would materialize might depend if there is correlation between what happens at different states on the vector x t minus 1, which does not appear here. So do you assume that? I mean, there is independence
I assume that the learner believe the states
are
independent.
Sorry, I had missed that. Sorry.
No, sorry, I didn't say it. I wrote it, but I didn't say it. Yes, the learner in this exam, for simplicity, nothing changes if we make it more complicated. You can take the Markov model, but then you still have the same issues.
Okay.
For simplicity, we assume that the learner believes the states are IID, and so these are just multinomial model with fixed parameters. And then everything goes. The truth can be whatever you want. It can be a deterministic sequence, it can be a Markov model, it can be whatever, whatever you want. But this is the model of the learner. If it so happens that the true is also IID and the probability is in the model, then it's well specified. Otherwise, it's misspecified. We don't make this assumption. Okay. Good. Now it's time to speak about time consistency. Time consistency is this beautiful property of Bayes' rule that tell us that if you take the probability that a Bayesian attaches to a cylinder, this can be calculated in two different ways. Either you take the time zero prior and you multiply and you use it to weight the unconditional probabilities on the same cylinder of each model, or you construct the predicted probability after one realization, and then you construct the predicted probability after two realization, etc. You multiply them. So here you go online. You make the first prediction, second prediction, third prediction, etc., etc., etc. The total probability you attach to the sequence is the same one that you would obtain if you just use the time zero prior and put the probability of the model in the support. So it's the same in terms of probability assignment to start from time zero and then make sequential predictions, or time at time zero and make prediction directly on an horizon t. Okay? This is time consistency. It's nice because if it fails, it can be arbitrages. Some people now might even define Bayes' rule as being time consistency. Because if the rule is time consistent, then you can find a set of models so that more or less you can claim that the thing is Bayesian. This is way too extreme. It's a long discussion we can have. In my opinion, this is way too extreme. In other community where people are a bit less ignorant about learning, it's well known that to say Bayesian doesn't mean much, in the sense that there have been counted more than 2,000 different ways in which you can be Bayesian. To me, in this paper, Bayes' rule means you start from a predefined set of models and you use Bayes' rule, this rule, to make predictions. You hear everything as being possible Bayesian method. I have to take a precise statement. Okay. Okay, now that we have defined Bayes' rule, I have no idea about the timing. I think I'm relatively okay. We can start talking about the various type of biases that people might have. The first type of biases we cover is the attitude toward time. There have been identified two different ways to make predictions. One is acceptive, meaning people make a predictive distribution about each next period realization, and then incorporate this information. And then when new information arrives, it makes, again, inference about the next period realization, but it's just one at a time. It's what in computer science is called online prediction tasks. You start with a prior, you have a realization, you make a posterior. You start with the posterior, you have a second realization, you make the second posterior, etc., etc., etc. This is acceptive. The alternative way is the pooling attitude. The pooling attitude is you start from the final horizon, you need to make a prediction, if you have it. Suppose you need to make prediction about sequence of length 50. So you use the prior and the likelihood of your model up to 50, and you construct this set of unconditional probability on that horizon. And then you reconstruct all the marginal by adding up the future nodes of the tree. That's very quickly. So if you have Hopefully they have the same number of nodes. So
everyone figuring out how to increase the size of that window, I guess.
But it's okay. It's not particularly. If you're acceptive, you do a forward looking approach. You start from here, you make prediction about here and here. Then if you land up here, you make prediction about here and here. Then if you land here, but here and here. And in this way, you construct all the probabilities. This is accepted, forward looking. The pooling one is backward looking. From here, you first attach all the final probability, and then you use the probability of subsequent node to get the probability of the nodes that are before, and you construct everything with backward induction. In the Bayesian approach, the two ways give you the same result. If you are not Bayesian, the two things give you different results. You can be acceptive, meaning you go forward, or you can be pooling, meaning you go backward. In experiment, people seems to be acceptive for the vast majority. Okay, good. Second bias, over and under inference. This is a standard model that dates back to Phillips and Edward, in fact, also a bit earlier, as usually happens, 1966. The idea is that the ratio of the posterior equals the ratio of the prior times the ratio of probability to the power C. If C is 1, this is Bayes' rule, because if you take Bayes' rule here, you take the ratio of posterior of different parameters, you would have that this simplifies, and you have that the ratio of posterior equal the ratio of the prior times the ratio of the probability. If C is greater than 1, then it's called over-inference. Suppose C equals 2, is as if instead of observing the probability of one realization, you observe two realizations. So you update faster. If C is less than 1, you update slower. So less than 1 under inference, you react slower than what a Bayesian would do when you change the relative weight of posteriors. C greater than 1, you react faster, and so you do over-inference, okay? Empirically, C less than 1 is what we have. It's consistent with conservatism bias. Good. Other bias that we can have is overreaction, underreaction. So this is still consistent with the empirical evidence of conservatism. So underreaction would be conservatism, overreaction is the opposite of conservatism in terms of what the name means. But this is a different analytical formalization of the same idea. It goes under a different name. This is the model introduced by Epstein, Sandroni, and Knorr in 2006, also axiomatized. And the idea is that the prior at T is a combination between the Bayesian prior at T minus 1, the Bayesian prior at T minus 1, here, and the Bayesian posterior at T. So BU mu T minus 1 xt is what a Bayesian posterior would be observing xt. Your posterior weight is a mixture between what the Bayesian would do and the prior of the Bayesian. So instead of moving between from mi t to mi t plus 1 here, it just update mixing with the prior. If you start with a prior which is 1/2 on the probability of head of a coin, and you see head, if you have suppose that the Bayesian posterior is to give weight 5/9 to head, the underreacting posterior would be, let's say alpha is 1/2, 1/2 5/9, 1/2, which was the prior before. You do not change the posterior as much as the Bayesian, and you mix it with the prior of the Bayesian. Okay? Empirically, we find underreaction, because underreaction is consistent with underinference. This is just a summary. So there is a very nice meta-analysis in Benjamin book 2019, and also obviously Kene Matvesky 2011. What we find is that people have an acceptive attitude, people do under-inference, people do under-reaction. These are other two possible interpretations. Let's forget about it for now. Tanto in an hour we don't have time. Okay. What is the rule that we propose? So this rule it depends on two parameters, the inference parameter C and the under-reacting parameter alpha. And it nests Bayes' rule as the special case in which C and alpha equals 1. The idea is that the predictive one step ahead distribution is going to be this C norm of the Bayesian. Here is to the 1 over C. It's, I don't know whether you see, I have all the faces here, that there should be a 1 over C here. Let me put it down. Yeah, okay, here, I see it. And the problem is that this C norm is doesn't sum to 1. No, these weights are prior, they sum to 1. These are probability. When you sum this guy, if C is different from 1, don't sum to 1. This is why we need to renormalize. How this the dynamic of this rule works? Well, the weight of the posterior equals the prior times the probability to the power C normalized by this factor. Okay? The normalization is needed, otherwise you don't sum to 1. The whole idea was to take, why it doesn't work? This equation here, so the under over inference, which come back here, because when you take the ratio, the denominator goes away and becomes the ratio between here. U and B, theta and theta prime is the ratio. Pardon me?
I have a question about the empirical summary.
Sí.
When you say that empirically people are acceptive, could you clarify what that means? Because under Bayesian updating, acceptive and the other one predict the same thing, right? They're the same,
exactly.
same model. So given that the predictions are the same, what does it mean that in the lab people are more acceptive?
Okay, so two steps. The first step is in the lab, people are not Bayesian.
Mm-hmm.
Given that people are not Bayesian, they make different prediction if you reveal them information in a way that is consistent with acceptive or in a way that is consistent with pooling.
Oh, okay. After inferring how under...
Now, these are all separated bias. They've been tested in a way that is not joint.
Okay, okay. Thank you.
Since people are not Bayesian, there is a difference between the two approaches, accepting and pooling. They made an experiment and they showed that people are acceptive.
Okay.
But I didn't make an experiment in which I fit this rule. I'm using a meta-analysis on the result of other experiments. Okay? Thanks. Okay, so this is the reaction component. When you take the ratio, the denominator goes away, and so what is left is this one, which is pretty much the over-under inference model, with the difference that now we have P rather than pi. And P is the mixture between pi and the predictive distribution itself. Why do we do that? Because I already proved in another paper that if C equals 1, this type of dynamic gives you exactly this time a posterior dynamics. So this one is over-under reaction, meaning this model for the evolution of the posterior. This one is over-under inference, this parameter here, this C here. This is the resulting probability. If we want a model that fits both underreaction, overreaction, over-inference, under-inference, this is the probability that come out. Okay? I have two extra parameters. Depending on the value of the parameter, I can decide, I can talk about 6 different biases. Over-inference, under-inference, underreaction, overreaction, and then the composition of these 4 biases with pooling and acceptive, so 8 different cases. Good.
So
Now,
to ask a question on behalf of maybe some other people, is sometimes people say, well, that looks like a very complicated rule. Are you cheating in some way? Is there another way to do it? You know what? Okay. Something I've heard.
That's very fair. Okay. First of all, the rule is complicated. Cognitively speaking, complicated. Without a computer, probably would be a pain to calculate with every C different than 1 and alpha different 1. But I just took the model from theory that have been used to describe that phenomena. So my approach was to start from a rule that have been proposed, but for which there is no asymptotic analysis or dynamic analysis on the long-run performance. So I didn't want to depart too much from the literature. I just want to, the approach is, there are these rules that have been proposed. I just put them together and I give you for every possible value of these parameters, whether they do better than Bayes or not, or worst. In terms of procedural rationality, ecological rationality, yes, this rule is obviously not a frugal rule or a rule that reduces the cognitive load on individuals. However, qualitatively, the proof technique that we use can fit every type of conservativist bias attitude. These are just analytically very tractable. They're not simple to calculate, but analytically very tractable. If you can come up with a rule of thumb that is easier to calculate and is consistent with underreaction, most likely the same result is going to apply. With the caveat that you do need to have convergence. Now, a simple rule is that just look at the last time realization. This is a form of underreaction. The problem is that whenever the truth is in the support, the Bayesian converges to the truth and you cannot converge because time realization are not enough. So this is a minimal rule that maintains the desiderata that is consistent, so it's not beaten by Bayes, and qualitatively is conservative, so it moves slower than Bayes. Whether it's the way people actually take decision, I'm sure that is not, because nobody would be so crazy to calculate this rule before taking a decision. It's capturing what is found experimentally. Okay? Yeah. Good. Okay, so C1A1 is a Bayes rule. C1, then the model is over under reaction. A1, the model is over under inference. So I wanted to have a rule that nested Bayes and the alternative rule that have been proposed. This is the rule that came out. It's too complicated. I'm sorry. The narrative could also be linked to a recent paper of Gigi Renzer, because typically the idea is that you have the Bayesian, which should be infinitely rational, and the cognitively limited agent, which is not. And then he was claiming that we have to make a distinction between bias that are useful to the fact that we have limited cognition and so help us to overcome this problem, and bias that are just damageful, because there is a large literature that just says bias are bad, and there are some biases that are bad. So this work here is a bit a case which is a third situation in which we compare infinitely rational agents. They can calculate whatever they want, but one is biased and the other one is not. And we show that in a large world, in a world that is complicated, to be biased is an advantage even if you are rationally, perfectly rational. No, because a lot of the rhetoric about biases is they come up with because you cannot calculate. In this paper, no, I assume you can calculate whatever you want, and I still show you that biases are good if the world is not simple. Not sure whether I answered, but I gave an answer. I'm not sure whether it was convincing. I proceed.
It's more convincing than I am when asked questions. So I think
so you gave me the bad question that people asked you in another occasion.
Basically,
Okay.
yes.
That's like referee do, no? You get a terrible referee or something you do, the next person that's doing something similar, same question. He might have been the referee. Good. Yeah, the idea is that this is a counterfactual, it's a theory paper in which we have infinitely rational agents, a complex world, and I show that in a complex world, even infinitely rational agents are better off not being Bayesian. Okay. Okay, now we have to talk about the comparison criterion. I introduced it before, what I wanted. Here I have a slide, so I just repeat myself. Hopefully it's gonna stick a bit more. The main idea I want you to capture here is that comparing learning algorithm when you do not make assumption about the truth is not trivial. Certain rules would just tell you that certain algorithms are better, certain other rule would tell you that other one are better, because you don't know what is the truth. We believe that the best way to give a criterion is to satisfy these 4 conditions. The first one is fair comparison. We say that a comparison is fair if let's say 2 learning algorithms use the same identical information. What is information? The same support. So the Bayesian, let's say Bayesian, and the non-Bayesian algorithm must use the same prior support, because otherwise we're not comparing 2 things that have the same input. So how can we say that one is better? The same times 0 prior, this is irrelevant because the condition is asymptotical, but still same information. And they must use the same history. So they must make update observing the same sequence. This is to give, this is very operational, like a computer scientist. You have a certain set of input, prior support, time 0 prior, and history, and you can choose, and you have to choose between 2 different algorithms. If you have different input, then you choose also on the input. So fair comparison. We must use the same information for all the algorithms. No cheating. We cannot make use of any properties of the true model, because otherwise, if we knew the true, we don't need to learn it. Again, this is a pragmatic perspective, like a computer scientist. You ask him to make predictions, he cannot tell you, well, if the truth is this one, then my algorithm works well. If the truth is that one, you don't need the algorithms. So we cannot make any statement about the truth. This is why you will not find in the paper many statements which are almost sure according to any probability, because we don't have the true probability. I'm working on every sequence, not on every probability. Relevance, okay, this seems obvious, but since we are economists, sometimes we do use odd criteria that are completely irrelevant. Relevance means it must capture something useful. In this case, likelihood ratio. I think likelihood ratio are a good standard in statistics. Truth-oriented, just to give a bit of structure, we do not want a learning algorithm that learn the truth. So in the case in which the model is well specified, learn the truth, to be dominated by another algorithm that doesn't learn the truth. I think is a good property, because, well, if we start with the true model and the support, I would like my rule to learn it. It's a desiderata. Okay? Good. So what is our criterion? We say that P star provides a universal advantage over prediction rule P, still under, yeah. if they use identical information, and on every path, the likelihood ratio between P star and P is strictly positive. So if we believe in likelihood ratio test, for example, P star will never be statistically discriminated against P. It never loses against P. And the second requirement is that sometimes P star must do better. So sometimes the likelihood ratio between P star and P diverges. If you want, you can put sequence rather than P tilde, because P tilde can be a Dirac on a sequence. So the main idea is that I don't know what's happening. I don't know which infinite sequence I'm gonna face. But I say that P star is better than P if P star over P never converges to zero, regardless of the sequence, for every possible sequence. And sometimes P star does much better than P because the ratio diverges.
Here it should be log of likelihood ratio, no?
If you put log, you have to put minus infinity and infinity. It's the same. Yes, if you prefer, you can put a log, but then here you have to put minus infinity rather than epsilon. Log 0 is minus infinity. So if you put log greater than 0 means greater than minus infinity.
Oh, I thought you meant to say P star is greater than P in the limit. That's not what you mean.
It's, well, this P star xt, they both converges to 0, right? The problem is the convergence rate. These are probabilities. So P xt is the product of P1, P2 given Px2 given x1, Px3 given x2, x1, etc., etc., etc. So this guy, they both converges to 0. This is why you have to take the ratio.
Mm-hmm.
No, this is a likelihood. The likelihood converges to 0. You have to see which likelihood converges to 0 the slowest. The one that converges to 0 the slowest is the one that attach higher likelihood and you like it.
So likelihood ratio in the limit should be greater than 1, no?
Greater than epsilon. I'm generous.
Okay.
Because at infinity, I don't want to enter all the literature about testing expert, because there is always this way to create a strategic prediction rule that with a certain probability do better at the beginning and then start copying, and then is always greater than 1. So here, they could be strategic algorithm, but I just put epsilon this way. We don't enter all these complications. Just 0 is obviously dominated. Greater than 0 is okay.
Okay. Got it.
Infinite is always better than the other one. And so this is pretty, it's generous in the likelihood ratio, meaning it's not too tight, but it's very general because I don't make any assumption about the sequence. So this is where the criterion has the bite, not in how tight is the condition. It's on the fact that you can feed here every sequence. No? Or the deterministic sequence, or this kind of stuff, or the ugly sequences, the non-converging sequences. You can feed here whatever you want. So, yeah. Okay, why we use likelihood ratio? Well, because most hypothesis testing is done using likelihood ratio, because if you do, I worked a lot in financial model of market, in which there is this market selection hypothesis, and what we always find is that if people use probabilistic model with a higher likelihood, they make more money. So likelihood and money go together. We are economists, we like likelihood. And also KL divergence is becoming the standard criterion in the literature in economics and computer science for misspecified learning. And the KL divergence is very similar to likelihood ratio. If the law large number applies, the KL divergence and the likelihood ratio give you the same ordering. So standard in economics, standard in statistics, standard in computer scientists, relevant for making money. I would say that the criterion is good enough in looking at likelihood. Okay? Now we are getting closer to the end. Let's see some results. I make it as compacted as possible because there are a lot of parameters. So let's read it together and try to understand what the theorem is saying. Suppose there is P star and P, which are parameterization of our sequential prediction rule. So this guy. They use the same prior, they look at the same sequence, but they have different parameter alpha and C. Then, for all prior supports, and for all prior, so for every possible set of model, for every possible prior, but they both use the same, obviously, the following table gives condition under which P star has a universal advantage over P. So, we read it left to right. It is win or green if this parameterization has a comparative universal advantage over this other parameterization. Obviously, if the parameters are the same, we don't say anything. So if we look at under reaction and under inference, they have a universal advantage over every parameterization for over inference or over reaction, every parameterization of alpha equals 1, including Bayes rule, and most parameterization with alpha less than 1. Here is complicated to give an analytical proof, but in simulation, we can at least make sure that this is not going to be better than this one. So this light green means we are sure that alpha minus 1, C minus 1 is better than C1 alpha minus 1 and C greater than 1 alpha minus 1. And in all the simulation we found is actually better. U is undefined, meaning sometimes it's better, sometimes it's worse, which is different than saying that we don't know. We know that there are sequences in which the thing works and sequences in which it doesn't. And red obviously means does worst. LS is loses with the simulation. These are just the mirror image of this one. This is letting alpha and C be as small as we want, as long as they're less than 1, or as big as we want, as large as as long as they're bigger than 1. Here we use a situation in which alpha is actually very small. Very big doesn't matter, but very small compared to C, a small of C. And qualitatively just become stronger. We just have that we eliminate some undefined with a thick green. Okay, now that we understood what the image means, let's get to the conclusion, the punchline. Alpha less than 1, C less than 1 does better than every other parameterization, meaning under reaction and under inference together are better than Bayes, are better than over inference and over reaction, and are better than any other possible combination of biases. So whatever we find experimentally, which is under reaction and under inference, is exactly the parameter choice under which our algorithm does better than all the other parameterization. This is why we call them good biases. Again, remember what the criteria tell us. The criteria tell us that if there must be no sequences in which this likelihood ratio goes to 0. So suppose that the Bayesian is correctly specified. Why I still put green? Well, because if the Bayesian is correctly specified, it will converge to the true model, but also the underreacting, under-inferencing learning rule converges to the true model. And the convergence rate is the same rate. They're both exponential. So even when Bayes' rule works the best, when it's correctly specified, the underreacting, under-inferencing rule doesn't lose much. This is why I keep it green, because the likelihood ratio remains greater than 0. Okay? On the other hand, when there are certain type of misspecification, you have that the under-inference under reacting rule does better than Bayes. Which type of misspecification? Well, when the truth is in the convex hull of the model in the support, so there is the possibility to mix the two models to get a model which is more accurate than every model in the support, and alpha is small enough. C effect is a bit more nuisance, so alpha is a first order in the description, especially in IID setting. Okay? So this is the intuition. Let's take away C. So suppose C is 1 and focus on the case of underreaction. Let's get the intuition. Here we have a model class which has only two models. There are two realizations, up and down. Two models. One has probability of up 0.4. The other one has probability of down 0.7. The true probability is 0.5, IID. So the true probability is this red line. The green line is the probability of model 1 of up, 0.4. The blue line is the probability of model 2 of up, 0.7. The red line, the black line, you should be able to see it because you have the computer. This black line here is Bayes rule. Bayes rule converges very fast to the most accurate model in the support, 0.4. This is a result known theoretically due to Berg. Bayes rule always converges to the model with the highest likelihood, or if you want, to the lowest scale divergence, which is the same. On the other hand, the gray line is the sequence of predictive distribution of the underreacting algorithm. Now you see that the posterior never concentrates. It always gives positive weight to both models. So unlike Bayes that converges fast to the best model in the support, underreaction never converges. And it fluctuates in such a way that is always closer to the truth, this point, this red line, than the best model in the support, this green line. This is why when alpha is less than 1, in this specific example, you have non-convergence, and you have that the underreacting algorithm does better than Bayes rule. Notice that Bayes always converges. If you take an IID environment, generically Bayes rule converges. The underreacting rule doesn't converge for potentially large interval in the support if alpha is small enough. And this is when it does better. Whenever the posterior doesn't converge of the underreacting algorithm, the underreacting algorithm is better than Bayes rule. This is why we have the turtle at the beginning. Underreaction does better because you don't get certain about a model which is not the true model. If you're a Bayesian, you always become certain about a model. But if the model is not the best one, maybe it's better to mix the model. No? In this case, you have two models. Probability of head 0.4, probability of head 0.7. The Bayesian, after few realization, becomes certain that the truth is 0.4. Too bad that the truth is 0.5. So it's better to remain a bit uncertain. It's better not to put all your egg in your basket. You want to give some credit to both models because the likelihood ratio is not as strongly indicating 0.4 as it should be. No? The Bayesian, since it's axiomatic, is fully bound by the logic of the likelihood ratios, but doesn't question itself. It doesn't realize that it's converging not as fast as it should. It still converges. The underreacting algorithm, whenever the convergence is low enough, stays non-convergent. So it gives positive weight even asymptotically. This is the main difference. So when does it happen? When the truth is in the convex hull of the support, but not in any model, and when alpha is small enough. Okay? Now we can also see the effect of alpha. No. What happened here? This is the sufficient condition. We don't have much time, and I already told you when it does better. When the truth is, yeah, here it doesn't state. Anyway, when the truth is in the convex hull of the support and alpha is small enough. And if this is true, this condition holds. Okay. This is to get an idea of the effect of alpha. This is simulation in the same environment, you have probability of up 0.4, probability of up 0.7 for model 1 and model 2 respectively, and you have different values of alpha. If you have Bayes rule, alpha equals 1, you concentrate on 0.4. This is a Dirac on 0.4. If you have alpha 0.2, you remain, this is the frequency. The prediction, the probability of the prediction are pretty much uniformly distributed between 0.4 and 0.6, which is better than 0.4 because the truth is 0.5. Then you make alpha smaller and you see that it starts to peak around 0.5. And if you make alpha very small, you converge to almost a Dirac on the true model. So the smaller the alpha, the more the posterior concentrate around a Dirac on the true frequency. This is why you can beat Bayes that stays on the best model. Okay? Good. Alpha greater than 1 doesn't work because this is just an example that shows that it becomes inconsistent. With alpha greater than 1, it might be the case that you converge to a model which is not the true model, even if the truth is in the support. We don't have the time to go to the example. This is an old result, actually, because for the case in which the learning is well specified, Epstein or Sandroni already found this result. Okay, so under-inference does better because it stays more in the middle, doesn't take completely polarized opinion, which is also very good in politics or any political related issue. And okay, this was for the accepting attitude. But we still have to talk about pooling. What happened with pooling? Our rule became this one. So we start from big T and we just use the time zero prior to weight the probability of the cylinder. And what happened with pooling is that the effect of every bias disappears. With pooling, according to our criterion, Bayes doesn't have a universal advantage over P for every value of alpha and C, and P doesn't have a universal advantage over P for every alpha and C. So with a pooling attitude, the likelihood enters inside the formula rather than being cumulated. And so the effect of this parameter is the same as a change in the time zero prior. So if the attitude were pooling, these biases would not do great harm or great good. However, since we know that the attitudes are acceptive, the theorem above tells us that the bias that we observe, so acceptive, under reaction, under inference, beats any other combination, and in particular beats Bayes' rule. And obviously, the acceptive beats pooling with under reaction and under inference. Probably I should put it somewhere. Okay. Conclusion, we have proposed a general rule whose parameter can be set to describe fit known bias. We have provided a fitness criterion for goodness of prediction rule under possibly misspecified environment. We have shown that biases that are predominant in the population provide an advantage according to this criterion, the one we introduced. And in particular, we have confirmed that an acceptive attitude, under reaction, and under inference are bias that help people make better decisions than they would do if they had if they were Bayesian or if they were having the opposite bias. Okay.
Oh, thank you very much. Shall
Good.
stop recording.